Assalamualaikum, hi everyone. So this is a video for chapter 7, Haloalkanes. In this video, we're going to discuss the subtopic 7.2 chemical properties of haloalkanes, and at the end of this lesson, you should be able to explain nucleophilic substitution reaction of haloalkanes, compare the relative reactivities of primary, secondary and tertiary haloalkanes towards hydrolysis and alcoholysis, explain elimination reaction in haloalkanes, explain the use of haloalkanes in the synthesis of Grignard reagent, RMGX with RARMGX, and also determine the structural formula of alkanes, alcohols and carboxylic acid prepared using the Grignard reagent. Now, let's start with the chemical properties of haloalkanes. So for haloalkanes, the first reaction that can occur is elimination reaction. Okay, so this elimination reaction, where we have an haloalkane, we react it with KOH, our strong base, in ethanol with heat, and we're going to produce an alkene. And also the side product HCl. So this reaction, we already learned it from chapter 5.2, preparation of alkenes. So the second type of reaction that we have for haloalkanes is nucleophilic substitution reaction. Okay, so this is our haloalkanes. Why we have nucleophilic substitution reaction? So as we discussed earlier, on our haloalkane, we have partially positive side and partially negative side. So this is the electrophilic side. Okay, so since we have electrophilic side on our alkyl group, where later we're going to have a carbocation, so nucleophile can attack the electrophilic side. Okay, so that's why when the reaction occur, so the nucleophile will attack the carbocation and this carbon-hydrogen bond will break. So nucleophile is substituting the halogens over here. So the product that we will get, so now the halogens is substituted by our nucleophile. And the side product, we will get the negative ions. We will get another nucleophile over here. So that's why we call it as a nucleophilic substitution reaction. We are substituting halogen with another nucleophile. So for our nucleophile, so this is for that, this is our haloalkane. This is the nucleophile. So this is the product, and X over here, the halogen, we call it as the leaving group. Okay, now for the nucleophile, we have two types of nucleophile over here. The first one, we have a strong nucleophile. And then the next one, second one, we have a weak nucleophile. How do we identify a strong nucleophile with a weak nucleophile? So it's easy. For strong nucleophile, it will come from anions. So the first one, you have over here your hydroxide ion, hydroxide. Hydroxide ion. Second one over here, negative OR. So this is what we call as the alkoxide ion. So why is it alkoxide ion? Because we have an alkyl group and then the oxygen over here. So the oxygen over here will be O minus. So this alkoxide ion, usually will come from salt. For example, CH3O and A. So this salt, it will dissociate to give us the alkoxide ion CH3O minus and then Na plus. So this is the source of your strong nucleophile. Next, we have over here Cn minus. So this Cn minus, or we call it as our cyanide ion. Okay, so this cyanide ion also came from salt. For example, okay, CN comes from NaCN. So as we know, salt will dissolve or will dissociate completely. So it will break, you will get Na plus and Cn minus. So Cn minus over here is our strong nucleophile. Okay, so that's for the strong nucleophile. For the weak nucleophile, as you can see over here, any nucleophile that doesn't have negative charge, we call it as the weak nucleophile. Okay, so for example, water. So where is the nucleophilic site? Okay, at the oxygen over here. It has lone pairs. So water is a weak nucleophile, and then here is our alcohol. Okay, hydroxyl group. So the nucleophilic site again is on the oxygen. Okay, oxygen has lone pairs. Okay, next ammonia. So your ammonia, or sometimes you can also use amine. Okay, so where's the nucleophilic site? It's on the nitrogen. Okay, and then lastly, we have over here, okay, CH3COO minus. Okay, so this is the only negatively charged nucleophile that belongs to the weak nucleophile. Okay, why is that so? So you will have over here C double bond O and then O minus. So there will be the electrons on the pi bond can be delocalized. Okay, it can so you will have a resonance structure over here. So CO minus double bond O. So due to the delocalization of the electrons between the two oxygens in this ion, the COO minus ion, okay, so that's why this one, okay, it will be a weak nucleophile because the electrons, the lone pair of electron is not readily being shared. Okay, so you need to make sure that you can identify the strong nucleophile and the weak nucleophile, because later when we do the mechanism, okay, we have two different mechanisms, SN1 and SN2. So the type of mechanism will depends on what is the nucleophile used and what is the type of haloalkane used. Now, let's look on the chemical reaction of haloalkanes. So, the first one, we have reaction with aqueous sodium hydroxide. So, if you look over here, all the reactants for reaction of alkanes, we will have a nucleophile. So, the first reaction over here, reaction with aqueous sodium hydroxide. So, this is your nucleophile. So, you need to be able to identify either we have a strong or weak nucleophile. Okay. So, this is the reaction. So, Rx plus OH. So, over here, sodium hydroxide, the nucleophile that we substitute with halogen is actually the OH minus. So, OH minus over here is your strong nucleophile. Okay, so strong nucleophile. So, the product that you will get is alcohol, and the leaving group will always be your halogens. Okay, so for example, CH3Cl. Okay, so over here, our Cl plus NaOH. Okay, so you need to be able to identify the nucleophile is actually only OH minus. So this OH minus will substitute Cl, and Cl will be the leaving group. Okay, so Cl minus over here, actually we can also write it down as NaCl. Okay, CH3, so the alkyl group. So this is the nucleophile. Okay, so the nucleophile is actually the hydroxide, and the leaving group is Cl minus. Okay, the second reaction, reaction with alkoxide ion. So for reaction with alkoxide ion, okay, so like I mentioned before, your alkoxide ion is this. Okay, and it will come from your salt. Okay, the dissociation of salt, and the product of reaction haloalkane with alkoxide ion is ether. Okay, so let's look at an example. So CH3CH2Br plus OCH3. So sometimes it will be written down as the ions itself, or at some other time it can also write down as NaOCH3. So it will be Na plus and OCH3 minus. Okay, or sometimes it is written down as CH3ONa. So CH3O minus and A plus. So it's the same thing. Okay, so this is the alkyl group. Okay, so this is your alkyl group. Okay, and then you will have mictoside as the nucleophile. Okay, so bromine over Br minus over here as the leaving group. So the methoxide over here will substitute bromine. Okay, so you will have a bond between CO and C. So that's why you will get an ether over here. Alkyl group, nucleophile, okay, and then the leaving group. So the third reaction is reaction with excess ammonia. Okay, so the nucleophile that we are using is ammonia NH3. So ammonia is a weak nucleophile. Okay, so this is the equation. So our haloalkane in excess ammonia. So when you are writing down the equation for reaction with ammonia, it must be written as ammonia excess. Okay, so we are going to substitute the halogens with the ammonia over here. Okay, but if you look over here, to substitute the alkyl group into the nitrogen, so you need to remove one hydrogen. Okay, so the product that you will get, okay, this is the amine, primary amine, and then we will get a mixture of salt over here. Okay, NH4 X minus, a salt over here. Okay, so for example, CH3, CH2, CH2Br. So this is our haloalkane. Okay, react with excess ammonia. So this is the alkyl group. So we have one bromopropane, the alkyl group. Okay, so to write down the product, so you will write down first the alkyl group. Oh, before that, this is our nucleophile. So ammonia is the nucleophile. Okay, so write down back the backbone, so the alkyl group, because the reaction will not occur there, and then substitute the nucleophile into the alkyl group and remove one hydrogen. Okay, because you need to remember nitrogen can only have 3 bonds and 1 lone pair. Okay, so that's why you need to remove one hydrogen, so that nitrogen will remain as 3 bonds. Okay, so the name of the compound is propanamine. Okay, and then you will get a salt of NH4Br. Okay, so Br minus over here is the leaving group. So reaction number 4 is reaction with KCN or NaCN. So the real nucleophile over here is your cyanide ion, Cn minus. So Cn minus is a strong nucleophile. Okay, so let's look at the equation. So the equation over here, haloalkane plus your cyanide ion. Cyanide ion is actually C triple bond N. The negative charge is on the carbon, not nitrogen. So that's why when we are drawing the bonding to replace the halogen, the alkyl group will bond to carbon. Okay, and then start this reaction. This reaction is important. Okay, so as you can see over here, okay, there will be increase in number of carbon. Okay, so let's say over here I have CH. Okay, let's look at one example. Okay, so CH3, CH2, Cl react with NaCl. So this is the alkyl group. So I have over here 1, 2 carbon. Okay, so we have chloroethane. Okay, react with sodium cyanide. Okay, so the alkyl group, sodium cyanide. Okay, what will be the product? So Cn minus is the nucleophile. So Cn minus will replace Cl over here. So the halogen, okay, will be the leaving group. So right now, if you look closely on the product over here, okay, so I want you to start this reaction, okay, because it is important. By addition of KCN, we will increase number of carbon by 1. Okay, because if you calculate over here the number of carbon, so initially on the haloalkane we have 2 carbon, okay, chloroethane. But right now we have 1, 2 and 3. So we have 3 carbon compounds. So we have increased the number of carbon by 1. Okay, so Cl minus is the leaving group. Okay, number 5, we're going to look on reaction with alcohol. So our alcohol over here, ROH, so it's a type of weak nucleophile. Okay, so for the general reaction, haloalkane plus alcohol, we're going to get ether. Okay, so X over here, halogen will be the leaving group. Okay, and then from the alcohol, okay, the alkyl group on the haloalkane will bond on the oxygen from the alcohol over here. So we're going to get a COC bond. Okay, meaning we have an ether. So for example, okay, I have 1-chloro-1,3-dimethyl cyclopentane. So I react it with a methanol. Okay, so what will be the product that we will get? Okay, so this is a leaving group, meaning we know that this bond will break and a nucleophile will be attached to this particular carbon. So from the methanol, okay, the carbon will be bonded to the oxygen over here. Okay, so that's why you will have OCH3. So it will break here. O over here is bonded to the carbon over here. And then the alkyl group next to the oxygen, you just write it down back. Okay, so this is the methyl group. So the methyl group will be fixed. Okay, sorry, the alkyl group, I mean. So this is the nucleophile, our alcohol. Okay, so the side product you will get HCl. Okay, and then from the HCl, the leaving group is actually our Cl minus. Okay, and then Cl minus will react with the hydrogen that's left behind from the methanol. Okay, the next one is reaction with acetate ion. So your acetate ion is actually C double bond O, O minus. So the acetate ion over here is a weak nucleophile. Okay, so this is the reaction. Okay, so as the alkoxide ion just now, okay, when we have halogen as the leaving group over here, okay, the O minus, the O from the acetate will bond to our alkyl group. So that's why you will get this structure RCOOCH3. So over here, the compound that we're going to get is an ester. So for example, CH3Br, okay, a bromomethane react with an acetate ion over here. Okay, so this acetate ion, it can come from CH3, C double bond O, O minus and A plus, a salt. Okay, so it dissociates, so you will get your acetate ion and sodium ion. So the connection, the bond, it will replace the bromine that will become the leaving group. Okay, so carbon, this carbon will be bonded to this oxygen. So that's why over here we have the new carbon oxygen bond, and since we have C double bond O, O and C, so over here, okay, so we have our ester. Okay, so the name is methyl acetate. Okay, and Br minus as the leaving group. Okay, so this is your alkyl group, this is your nucleophile, and then this is the leaving group. Okay, next we're going to look on the reaction with water. Okay, so remember water over here is the nucleophile, so it's a weak nucleophile. Okay, so weak nucleophile, so this is the reaction. Okay, so your haloalkane plus water, we're going to get alcohol over here. Okay, so for example, CH3, CHBr, CH3. Okay, so if I were to write down back the structure, CH3, CH, so Br over here, CH3. Okay, so we're going to remove this bromine, we're going to substitute with the OH from our water, okay, to get our alcohol. So Br will be the leaving group. So this is the alkyl group. So for the 2-bromopropane, okay, and the product that you will get over here is this one. So if I were to write down back the product, so CH3, CH, CH3, and then on this particular carbon, okay, we have our hydroxyl group. Okay, because we already substitute bromine over here with OH. That particular OH, where does it come from? It comes from water over here. Okay, so we have 2-propanol as the product. Okay, alkyl group, the nucleophile, okay, and the leaving group. Okay, the leaving group here is actually our Br minus, leaving group over here. Now, we're going to look on the synthesis of a Grignard reagent. So Grignard reagent is one of the most important part of haloalkanes. Okay, synthesis of Grignard reagent. Okay, reactant is alkyl or aryl halide. So if we have an aryl halide over here, meaning it is our benzene with halogen. So this is aryl halides. And then to produce the Grignard reagent, our haloalkane will react with magnesium. Okay, so the condition, it must be in dry ether because we don't want any water present. Okay, so this will be the reaction. So Rx, our haloalkane, react with magnesium in dry ether to produce the Grignard reagent. So this is our Grignard. Okay, so why is this Grignard reagent important? Okay, by adding magnesium to the haloalkane, what can we produce? So initially, R over here is partially positive. The carbon is partially positive and the halogen is partially negative. Okay, if we want electrophile to be inserted, okay, with the R over here, by adding magnesium, what will happen is the alkyl group over here will become partially negative because carbon is more electronegative than magnesium. So magnesium over here will be partially positive. Okay, so X is your halogen, either Cl, bromine or iodine. Okay, so this is the Grignard reagent, partially negative, partially positive. Okay, uses of Grignard reagent. So this Grignard reagent can be used in 3 different ways. The first one, reaction of Grignard reagent with water, we're going to get an alkane. Second, reaction of Grignard reagent, KRMgX, with carbonyl compound and also acidify, 2-step reaction at carbonyl. This carbonyl compound actually must be added in dry ether. Okay, and then we're going to acidify the reaction. We're going to get alcohols. Okay, we will get different alcohols. Okay, next. Okay, the third one is 2-step reaction as well. Grignard reagent react with carbon dioxide, and then the second step we acidify to get our carboxylic acid. So now let's take a look one by one. So in synthesis of alkanes, okay, so what happened here is we will have our Grignard reagent react with water. So how does the reaction occur? How does alkane is produced? So R over here, okay, will be partially negative and magnesium will be partially positive. So from the water itself, okay, you will have a nucleophilic site over here, electrophilic site. Okay, so this bond will break, okay, and then it will take the hydrogens over here. Okay, and then OH will also break. So that's why over here R will be bonded to hydrogen. Okay, here. So you will get your alkane, and then the rest of the salts over here, MgX. So actually the first thing that occur is this magnesium and carbon bond will break. The two electrons will be attracted to carbon. Okay, and then that electron that is attracted to carbon, then okay, it will take the hydrogen over here. So that's why you will get an alkane, and then salt over here. So for example, okay, so this structure, so you're going to focus on the last bit part over here. Okay, so plus with H2O. So what's going to happen is, okay, this Mg-Br bond will break, and the C over here will become C minus, a carbon ion. So that carbon ion will take the hydrogen. Okay, HOH. So the carbon ion over here will take the hydrogen. So it will form alkane at the end of here. It will form the carbon-hydrogen bond. Okay, so we will get hexene. Next, we're going to discuss the use of Grignard reagent in synthesis of alcohol. So for synthesis of alcohol, by using Grignard reagent, we can get a desirable alcohol, meaning we can specifically form a primary, secondary, and tertiary alcohol. Okay, so how do we do that? So this is our Grignard reagent. Okay, so from the Grignard reagent, so let's label. So this is partially negative, this is partially positive, and the bond will break over here. Okay, so the Grignard reagent. So first one, if we want to produce a primary alcohol, so primary alcohol can be produced by using, okay, over here, a methanol. Okay, so methanol will give you a primary alcohol. How? Okay, so it must be done in ether. Okay, and then second step, acidify. So this will be the product that will form. Okay, so if you look over here, so let me label the carbon on the alkyl group over here as carbon number 1. Okay, and on the carbonyl over here as carbon number 2. Okay, so why this 2 carbon is important? Okay, because this 2 carbon over here will be the site where you're going to form a new carbon bond. Okay, so over here, what will happen is from the methanol, from this methanol, you will draw it back. Okay, H and then H, and then the carbon double bond O over here, remove one bond and leave it as OH. Okay, so at this carbon, it will be bonded to the alkyl group from the Grignard reagent. So whatever carbon it is, okay, whatever alkyl group you have. So over here, you will certainly get a primary alcohol. Okay, next, if you want to produce a secondary alcohol, the reagent that you need to have is, okay, so we need to use aldehyde. Okay, any aldehyde besides than methanol. Methanol is also an aldehyde, a 1 carbon aldehyde. So for secondary alcohol, use an aldehyde starting from ethanol. Okay, so same goes. So this will be the second carbon. So this carbon, this particular carbon, will be bonded to your alkyl group. So the reaction must be done first step in ether, second step acidify. Okay, so this will be the product. So you will get a secondary alcohol. Why? Because this carbon right now is bonded to 2 carbon. So it's a secondary carbon. So you will have a secondary alcohol over here. And then where's the part of the new bond form? Okay, so this is, okay, so if I were to draw for you, okay, from the aldehyde, okay, over here from the aldehyde, okay, so you will draw R, okay, any alkyl group. So here at the carbon-carbon double bond over here, single bond OH. So this particular carbon, carbon number 2, okay, will be bonded to carbon number 1 from the alkyl group, from the Grignard. Okay, so that's how you do a new connection. Next, if we want to produce a tertiary alcohol, so we're going to add over here ketone. Okay, so this will be carbon number 2. Carbon number 1 is from your Grignard reagent. Same condition in ether and then acidify. So you will get a tertiary alcohol. Why? Because this carbon is bonded to 1, 2, 3 other carbons. So it's a tertiary carbon. So you will get a tertiary alcohol. Okay, so same goes over here. To draw the product, to draw the tertiary alcohol, so you first draw the structure of your ketone. So R, C, R. So any alkyl group, okay, over here. So this is the second carbon. Okay, this second carbon is bonded to oxygen. So it will become OH over here. And at this particular carbon, number 2 carbon over here, okay, so you will bond with the alkyl group from the Grignard reagent over here. Okay, so this is where the new carbon bond is formed. Okay, so for example, I have CH3MgCl, okay, a Grignard reagent, and then I react with methanol. Okay, so this is one carbon, so this is carbon 1, this is carbon 2. Or if I do it as the one that I did just now, this is carbon 1, this is carbon 2. Okay, so to draw the product, you know that the bond will break over here. Okay, so you will draw carbon 1 first. Carbon 1 that is bonded to hydrogen. So just put as CH3. So this particular carbon number 1 will be bonded to this carbon. Okay, so that carbon number 2. So that particular carbon number 2 is bonded to hydrogen, hydrogen, and then double bond O will become single bond O and then H. So you will get your primary alcohol over here. So formaldehyde. Okay, so this is your structure. Okay, so if it's this one. Okay, let's say I give you another example. Okay, still the same Grignard reagent. Okay, I add with a ketone. C double bond O, CH3, CH3, CH2. Okay, so here will be the site for carbon number 2. Okay, so the product, okay, you can start by drawing this one first. Okay, so CH3, CH2, C, CH3. So this is your carbon number 2. Okay, at this carbon number 2, it is bonded to initially double bond O, so it becomes OH. Single bond O and then H. Okay, next, this carbon number 2 will be bonded to carbon number 1 over here. Okay, so bond CH3. Okay, so from this one, since this is a ketone, so you will get over here a tertiary alcohol. Okay, this is just now, okay, our first carbon. First carbon that came from the Grignard reagent. Second carbon, second structure came from the ketone. Okay, now lastly, we have for synthesis of carboxylic acid. Okay, the last use of Grignard reagent. So for carboxylic acid, to produce, okay, we need our Grignard reagent and then two-step reaction. First, we're going to add carbon dioxide. The second reaction, we're going to acidify. Okay, so what you're going to do is, okay, so this is an example. So we have our Grignard reagent over here. So all of this one is your alkyl group. So this is the MgX. So let me label this carbon. So this will be carbon number 1. Okay, carbon number 1. So the bond will break here. So that particular bond will be bonded to the carbon dioxide HD. So your carbon dioxide, as you know, is this structure. Okay, C double bond O like this. So this will be carbon number 2. So to draw your product, okay, CO2 H3O+. Okay, the first thing that you need to draw is this one. Okay, meaning you're going to draw back. Okay, you break the bond over here and then you draw, okay, whatever that's left. Okay, without changing anything. CH3, CH3. Okay, and then at the side where you break the bond, okay, you don't have to think much. So by right, this structure will go into here. So as simple as just put COOH. Okay, COH is C double bond O, OH. So what happened actually, one of D double bond O is changed into OH over here. Okay, and then the other one, the carbon will be bonded to the one from your Grignard reagent over here. So you will get right here your carboxylic acid. Okay, so 2,2-dimethyl propanoic acid. Okay, so that's all for the reactions of haloalkane. So after you have finished this video, what I want you to do is make a mind map that combines all the reactions of haloalkane. So you need to have the elimination reaction and then nucleophilic substitution reaction. And then in the same mind map, okay, include as well the reaction for your Grignard reagent. How to prepare the Grignard reagent and then the use of Grignard reagent. Okay, so that's all for now. Thank you for listening. Bye.